Hello and welcome to SETI Live. I'm your host, Beth Johnson, Communication Specialist here at the SETI Institute. Joining me today is Ben Fernando, who is the lead author on a new paper about a very particular, very large Marsquake. Welcome in, Ben. Thank you for joining us. How are you doing today?
Great, thank you. How are you?
I am good. I love this paper. Let's get right into it. Everybody, obviously welcome into the show. Tell us where you're watching from, but we're going to try something new and we're going to get right into the science. So Ben, tell us about this Marsquake. How big was this Marsquake and why is it special?
So this Marsquake was the largest one that we ever saw on Mars with the InSight lander, which operated there from 2018 until 2022. And it was a magnitude 4.7 quake. So not large compared to the biggest quakes you get on Earth, but if you live most places in Europe, on the east coast of the US, it's about the largest quake that you'd ever likely get there. It was also, several times larger than the next largest Mars quake that we saw. And whilst it probably wouldn't have been enough to bring your house down if you lived on Mars, it was large enough that it would probably have woken you up and you would have been a little bit surprised to find things shaking.
I live in California, so I am very familiar with the whole concept of earthquakes, of course. And yeah, 4.7 would get my attention. It would not scare me, but it would definitely get my
Mhm.
attention. We don't really dive under tables for anything less than a 5 around here. But so you said that this is slight. It was bigger than the other. There were two other large ones that were
Mhm.
also measured during this time period. How big were those two? And can you kind of explain to the audience, like, logarithmic scales are a little difficult to comprehend for some of us. Can you kind of
Yeah.
like explain how much bigger that 4.7 was than those?
We measure the strength, the energy release of earthquakes using something called the moment magnitude scale. If you live in California, you might know it as the Richter scale. The two are similar but not identical. And it's what, as you said, is a logarithmic scale. And what that means is if you go from a magnitude 5 earthquake to a magnitude 6 earthquake, it's not just, going up by a factor of 2 or something. For each power that you go up by, it's not like you just multiply, you're actually going up by 10 to that power. So, for example, a magnitude 6 earthquake is many times more powerful than a magnitude 3 earthquake, not just twice as powerful. So it can be a
Mhm.
little bit counterintuitive, but it means that, this magnitude 5 earthquake, other earthquakes or Mars quakes that we measured, I should say, on Mars, magnitude 4 and below. So this was really several times larger than almost all of the other events. The two that was kind of not similar, but getting up there in terms of size that you mentioned were two that we also detected with InSight. And the really interesting thing about those two is they were both caused not by the same things that cause earthquakes in California, but
Mm.
by impact events. So meteoroids striking the surface. And as you can imagine, that stuff, it's coming in from space, remnants of an old comet, asteroid, whatever it might be, hits the surface going so fast, instantaneously vaporizes, forms this huge crater. And that crater, the formation, gives off lots of seismic waves. And we detect those with InSight. And that was a really interesting thing, is the only things that came close to this quake in terms of energy release were the two impact events.
So how did they know that those two events were impact events? How did they figure that out?
So it's kind of a bit old fashioned in a way. We basically take lots of images of the surface of Mars. And what we do is occasionally, when there's a big impact event, you see a new crater form. Normally, they're pretty small. And so you wouldn't notice them from day to day. But those two were so large. And the blast zone, so if you like, the area around the immediate crater was so big that it was actually visible in kind of the weather camera images that we take of the surface of Mars, if you like. So it was pretty obvious from the surface that this big new black area had formed. And from that, we were able to date the craters to plus or minus a day. And we could see that it lined up exactly with when we detected these Mars quakes.
That's fantastic. So again, kind of referring back to California, we're over here sitting on a transform boundary. We have, earthquakes regularly. Not necessarily large ones, but we have plate tectonics on Earth. We understand the mechanics of earthquakes here, but we don't have plate tectonics on other planets in our solar system that we have ever found yet. But definitely, we're pretty sure not on Mars. Again, as you said, we take pictures of that surface all the time. There's nothing identifying plate boundaries or anything like that. So a lot of these quakes are obviously coming from something different. And you said the two big ones that had already been determined were from impacts. So tell us what is different about this big one, as we've called it, that you found, your team. And when I say team, everybody, you have to understand this is a huge collaboration amongst a whole bunch. There are so many things out at Mars taking pictures all the time, and every single organization that has an observer looked. So Ben, tell us the story behind that. How did you get all of these groups together, and what did you find?
Yeah, it was pretty hard work, to be honest. So those groups, some of them we work quite closely with on a regular basis. Obviously, the other NASA missions like InSight, we speak to all the time. The
Mhm.
European mission, so the ExoMars Trace Gas Orbiter, we work with quite a lot as well. But the Indian and Chinese and UAE space agencies, although we're aware and sometimes we know the scientists working on those projects, it's not like we have regular or daily, weekly contact with them at all. But for this project, it was so important that we get a wide sort of image of the surface of Mars. We take lots of pictures across the entire surface, that we really had to call on our partners overseas to collaborate with us on this particular exercise. And that was, one of the main challenges here was just coming up with a way of collecting all that data, telling people where we wanted them to look, and then, processing those images and making sure we were able to exclude the presence of a new crater anywhere else in those images as well.
So you said exclude the presence of a new crater, and we will get to that. But how big of a crater were you looking for? That's kind of one of the amazing parts of this. So those two that we talked about before left craters of a particular size. And so when you started thinking about this bigger seismic event,
Mhm.
obviously you're thinking, okay, it has to be a bigger impact if it's an impact. And so what was the difference between what you had found before and what you were looking for this one?
Yeah, really good question. I think one of the challenges is that we don't have a good sort of way of judging how large the event would have been, simply because we'd never seen any events this large on Mars before. So we can apply what we call a scaling. So it's a bit like saying, a 10-meter crater is probably, more than 10 times the energy of a 1-meter crater. And, maybe it's more like 50 times. But we don't have any craters that we'd seen form that would have been of this energy. And we were thinking it would probably have been somewhere in the sort of 3 to 500 meters in diameter range. And that would have produced a blast zone that would probably have been at least 100 kilometers across. So what is that, 1,200, 1,300 feet, and then a blast zone that was probably 60, 70 miles across. But we, didn't see anything even comparable to that. So it was
Mhm.
a good indicator very quickly that there was no big crater. What we also wanted to exclude was the possibility that something could exploded in the atmosphere. So sometimes these impacts, as they're coming in, they're heated so much that they explode in the atmosphere, and that doesn't leave you a big crater, but it does produce a really strong seismic signal as well.
And that is an interesting point too, because a lot of people may have the impression that Mars doesn't have an atmosphere, but it does. It's not as thick as Earth's, obviously, but it can still slow down an impact. It can still cause things to explode.
Mhm.
So that was still a possibility for you, was that the atmosphere had done its job and protected the surface of the planet.
Yes, absolutely. So the Earth's atmosphere is, 100 or so times as dense as Mars is. But even that little tenuous atmosphere on Mars is still enough to support wind, to support dust storms, and yeah, even to slow down these things coming in enough that they explode because they get so hot.
All right. So you have a bunch of organizations and everybody is looking for signs of this crater, this blast zone, and you don't find it. So
Mhm.
what does that lead you to consider about Mars?
So the only other opportunity, possibility that we could think of where this crater had come from, that it was a tectonic event. So actually, not a million miles different from the sorts of things you get in California, and not an impact event at all. And if you can imagine, the biggest events that you see in California are related to how seismically active they are. You get really big earthquakes in California. You don't get very big earthquakes here in Maryland. But you can kind of think about that over time as well. If you see a really big earthquake, it means exactly the same thing as seeing a really big Marsquake. It confirms to you that the area is more seismically active than perhaps you would have imagined before. So the fact that this was a really big event confirms to us that actually Mars was about as seismically active as some of our predictions before the landing, before InSight had even got there, had suggested. But if it hadn't been for this event, we might have thought, well, actually, maybe it's quite a bit less active because we haven't seen anything nearly as large.
And remind me and the audience, how many months of data did we get from InSight before sadly the mission ended?
So we got a couple of Mars years worth of data, and a Mars year is 687 Earth days. So from about the spring of 2019 through to 2020, 2021, we were recording almost continuously, so the seismometer was always on. And then as the dust started to affect the solar panels more and more, we started to switch the seismometer off. At this point in 2022, when this event happened, the seismometer was only recording, I want to say, probably less than half the time. So we
Mm.
actually got really lucky that we even happened to record this Marsquake, and naturally ask the question, how many did we miss in the noisy period as well?
And so why okay, so we don't have plate tectonics. It wasn't an impact. What is happening below the surface of Mars that could have caused this?
So Mars doesn't have plate tectonics, but it's still geologically active. So we suspect the outer core is still liquid. There's still plenty of heat being generated from radioactive decay deep inside, and that heat worms its way up to the surface very, very slowly. So although the surface doesn't have these, plates sitting on a convective mantle in the same way that the Earth does, it's still got that heat inside which can
Mhm.
can move things. There's been suggestions that there's still some residual volcanic activity below the surface, and of course, the planet's still cooling. All of that heat escapes out into space. And as that happens, the planet cools and it shrinks very, very gradually. So that's an additional source of stress that builds up in the crust and is eventually released, we think, in large part through Marsquakes.
Wow, that is amazing. So this was sort of a bit of luck for
Mhm.
getting this earthquake, this Marsquake, and a lot of hours looking through images. How long did it take the teams to sort of go through the images before you reached the conclusion that no, there wasn't an impact?
It took a couple months, but that was also because it wasn't just a case of we take all the images today and look at them tomorrow. We've got only a handful of spacecraft in orbit around Mars, and they're limited in where they can image on the surface by where in their orbit they are at that time.
Mhm.
So what we had to do is some of the images, we were acquiring very quickly, very rapidly, but other things we had to specifically command spacecraft to turn and take an image of the regions that we wanted. And that took, many more weeks to months. And then, of course, analyzing that data took several months as well, just because, there's so many different steps involved in figuring out where you want to look, which we did
Mhm.
from the seismic data, then choosing image area, sending those coordinates off. People have to wait till they're at the right point in the orbit to take the pictures. They send that data back to Earth. It has to be processed, and then we can finally look at the images.
So did you determine where the impact might have been, like the probabilities? Here it's you triangulate to where,
Mhm.
the earthquake epicenter was, but how do you do that on Mars when you just have InSight and one seismometer?
So it's a lot harder, actually. One of the challenges is that, as you say, you've only got a single station, but there are still things that you can do. So, for example, earthquakes, Marsquakes, they produce P waves. Those are pressure waves, just like the sound waves in the room, and S waves, which are transverse waves. They're a bit more wiggly. They look a bit more like waves on the surface of water, even though they're actually quite
Mhm.
different. And they propagate at different speeds. P waves propagate a couple times faster than S waves. So what you can do is you can use the difference between how long the P wave takes to get to you and how long the S wave takes to get to you to come up with a rough estimate of how far away the event might have been. And there's a couple other neat seismic tricks you can do with data like that, using also what we call surface waves. So those are seismic waves that propagate very close to the crust of the planet. They're the things that do all the damage in places like San Francisco and Los Angeles when they occur. And with that, we were able to kind of pin down a rough area of where we wanted to look, but it's still a huge area that's, several hundred miles by several hundred miles.
That is an amazing amount of work and an amazing amount of detail and collaboration. How did it feel sort of organizing this, getting this collaboration together? That is that it seems, just like from the list that I saw from the paper, that seems like a massive undertaking in and of itself.
Yeah, absolutely. And even once we'd done that work, we had to deal with the fact that, not all of the images have the same resolution. So it's like taking images with a 2010s camera phone and a 2023 camera phone. Some of them are much more detailed than others. Some of them cover a much wider area than others. So honestly, the hardest thing in this paper was probably the logistics. So really figuring out how to make sure we got all of those images together into one paper, and then running with that to come up with a map of, what areas we'd searched, and then eventually to conclude that there was no Mars, no new sort of impact crater that had caused this Marsquake there.
I have to ask sort of the personal question here. How excited were you at the result? Like, what did this mean for you? How did it make you feel?
It was pretty cool. I can't lie, though. I actually study impact processes. So, in a way, I would have loved if this had been an impact event, because it would have been so off the scale large in terms of what we'd seen before, or even what we were expecting, that it would have been a really useful data point in our studies of impact processes. But at the end of the day, it was still a super cool result. We got to work with a huge number of people from all across the world. So, it was a pretty chuffed with it by the end of the day.
Oh, that's fantastic. Do you think that you'll be able to do this kind of collaboration again, or does this feel like this was kind of a once in a lifetime thing?
I think it's going to be a challenge simply because we don't have any other events from inside of this type to look for, and also there are no you know sort of fresh impacts happening that we know of anymore at this scale, because we don't have a seismometer on the surface. So I don't know how long it will take until we get another seismometer on the surface of Mars. I'm guessing at least 10 to 20 years, but it'll be pretty cool when it does happen. We just have to look for other places. We're working on seismic missions to the moon, to Saturn's moon Titan now, which will be very different to what we see, on Mars. But we won't be able to call on spacecraft orbiting in the same way to take pictures. So yes, we'll keep the collaboration going, but we'll have to do it in a very different way to what we do at the moment.
I'm excited to see where all of this goes. I'm going to take some questions from our audience because we have had some come in, and there are a few that I really kind of want to touch on here. So David Murphy is asking, how do we know that the quake was real and not an instrument error?
So yeah, really good question. We know what Marsquakes look like, not just from a single Marsquake, but because we've had more than 1,000 of them occurring over the course of the mission, and they don't all look the same, but they look very, very different from the instrument errors that we see, which are sort of smaller glitches in the electronics. These instruments are also incredibly well calibrated, so it's not like the sensor on your phone. Even they're far more sophisticated than some of the best seismometers that you would find, just sort of in most places in California. Even they've been very carefully calibrated and tested by NASA and by the contractors who built them. So we can be very certain that this wasn't an error. Also, the fact it was so large means it stands out a lot above the background noise, and there's no question of whether it might have just been unusually noisy that day or something.
Okay, that makes sense. Um, Stephen Collins is asking, he's asked a lot of questions, and I think I've covered most of them. Would the next landers have a seismograph? Would that clearly advance the science results of these Mars quake
Yeah.
studies?
So I think one of the wonderful things about seismology is it's really just a case of the more you listen, the more you learn. These things happen randomly, but we know that the big ones happen less frequently, though still randomly for the small ones. So I probably wouldn't want to go back to the same place on Mars with a single seismometer, but what might be cool would be to go back with, say, 3 seismometers. So then you can start to do triangulation, or to
Mhm.
go to one of the places on Mars where we think we've detected regular seismic activity, to see if we can understand a little bit more about what might be causing that, and whether it's tectonic stresses, or it's magma under the surface, or whatnot. So yeah, it would be really cool to go back to Mars with more sophisticated seismometers than we've got at the moment. But as I say, there's no plans at present to do that. Certainly, no one's proposed sort of missions that have got funding to do that yet.
Um, yeah, that's always going to be the challenge, is the funding aspects of everything. Um, Brad is asking, how often would you estimate impacts of magnitude happen, like the Antarctic meteorite that was traced back to Mars? How, I know we have only like a very small sample, really, of Mars quakes, but did it kind of give you like a breakdown of, how frequently certain types of events seem to be occurring on Mars?
It did, but only for the things that happen regularly. So speculating on things that happen less frequently than every 5 years using InSight data isn't really robust. So you imagine it's like it would be like trying to guess how often the buses come on your street, but trying to say, how often the buses come on a 10-year timescale wouldn't really be as meaningful because you only have experience from the hours, days, months that you've lived there. So, how often do impacts of that size happen that are large enough to throw a projector that escapes Mars's gravity? Um, I think you'd be looking maybe in the hundreds of years, but I suspect more like thousands, tens of thousands of years, because Mars isn't as big as the Earth, but it's still got a pretty hefty gravitational field. So it's unlikely that a small impact will throw something out hard enough that it will escape Mars's gravitational field. But Mars hasn't really changed a huge amount in the last couple billion years, so the surface is covered in craters. Over time, a substantial volume of the Martian surface has been ejected out into space. So it's very cool when we find it on Earth, but there's probably quite a lot more meteorites from Mars on the surface of Earth. It's just sometimes can be quite challenging to identify them as coming from Mars because it takes quite a detailed chemical analysis to be able to do that.
That makes a lot of sense. Again, living in California, the paleo seismology that has been done
Mhm.
to sort of see what the probabilities are of things occurring on certain timescales is about as narrow as you can get it down to from, a tectonic standpoint. So I can understand that. Yeah, no, without all of the data, you can't really make any sort of prediction there. What is next for you? What are you working on now? What's in your future? I know you are currently stateside at the moment.
Mhm.
So, what's going on for you?
So the next couple big things that will happen is there's a series of missions going to the moon at the end of this decade, which will carry one of them will carry a seismometer, that's a far side seismic suite. The other one that I'm working on is called Viper, which won't have a seismometer, but it will have a very sensitive measurement unit and a drill. So we're hoping to use the drill as kind of an active seismic source to try and detect what we might see if we were actively drilling into what we will see if we're actively drilling into the lunar subsurface at the South Pole, which is a place where we think it's entirely possible there's quite a lot of water ice hidden below the
Right.
surface. Longer term, I'm also working on the Dragonfly mission to Titan, so that will carry a seismometer to look at the structure of Titan. Titan's an icy world, an ocean world. It's got a thin layer of ice over the surface and then a global water ocean, which is really interesting from a sort of astrobiology habitability perspective. But that's much longer term. We're not going to get there until the mid 2030s. So at the moment, we're still very much in preparation. They haven't actually started building most of the spacecraft yet, but that's what's for me on the long term cards as well.
Planetary science is a long game. It is not an instant gratification study. Uh, and if anybody has seen them, I have been tweeting them out, but they are doing testing of a half-size dragonfly
Mhm.
drone, and it is that alone is amazing to see right now.
Yes, we had the
And
Dragonfly team meeting this week, and it was pretty cool to see the drone flying videos.
yeah, that was really neat, and I'm really excited. I'm excited for you that you get to be working on that particular mission as well as Viper. I've been reading up on Viper a bit in the last few months as well. So that is incredible, and good luck on that. Congrats on this paper and the fact that this was such a huge collaboration.
Thank you.
Amazing work and congratulations. And so thank you for being here, Ben, and talking to us today. Um, you did a fabulous job of answering questions. I understood everything, and that is fantastic. And I've seen some comments from everybody else that it was really good. So thank you for joining us, everybody. Thank you for watching. I just want to give a few shout outs here. People were watching from New Jersey, from Germany, from North Carolina, from Louisiana, more Germany, Texas, New Hampshire, Brazil, Sweden. I saw another one, Pakistan. Wow, I'm all over the world, and it's fantastic. So, thank you everybody for joining us. Thank you, Ben, for being here today, for taking time. And, everybody go off and ask questions in the comments, and we will do our best to answer them for you. We'll see you guys all next week. I'm going to be talking, I believe it's a SETI one. I'd have to check my schedule, but we'll be back again next week to do this all again. So thank you, everybody, for being here. And Ben, thank you for joining us.
Thank you.